Swayamprabha. Digital India. Educated India.
Welcome again to this course on CFD. This class is module 5 for this week. We have seen so far illustration on the performance by different interpolation scheme for convection term, time advancement, different methods in the time advancement, arrangement of variables in particular, 3 different arrangements we have seen, and then need for pressure velocity coupling. It described why one has to go for this pressure velocity coupling procedure. We listed 4 procedure. Out of the 4 procedure, last class we have particularly seen a method called marker and cell method, MAC. So, this class we will focus on another method, what is known as a simple method. For the sake of continuity, we will try to understand once again what is pressure velocity coupling. So, in governing equations, there are 3 governing equations, one for each velocity component, and you have one continuity equation. There are 3 variables for 3 velocity and 1 for pressure. So, in total there are 4 variables, number of equations 4, number of variables 4, hence it is satisfied. Though pressure appears in each term, there is no separate equation for pressure, and pressure derivative plays important role in each momentum equation. However, velocities term appear in each equation and they are strongly coupled. So, there is linkage to connect between pressure and velocity through these 4 equations is established by a procedure what is known as a pressure velocity coupling procedure. So, in this particular class we are going to look at a scheme called simple scheme. Before going to the detail, let us first understand what is again staggered arrangement. In this figure you see vertical lines, thick vertical lines, and then you are also able to see dash vertical lines. In between 2 thick vertical lines you are able to see dash vertical lines. Similarly, horizontal lines you get thick horizontal lines and there is another thick horizontal line, and then there is a dashed line in between horizontal lines. Here also you can see a dashed line in between 2 horizontal lines, on the other side also you are able to see. We have already seen staggered grid, velocity variables itself are stored at staggered location and pressure or any other scalar is stored in some other location. So, what is shown here is a first U cell that is marked in the red color and that is at one location, then V cell is marked here and then P cell is marked here. So, each variables are stored at different location and pressure cell is at different location. Simple algorithm that we are going to talk about in this class is specifically explained for staggered arrangement. Now, this figure is repeated in the next slide, the nodal information also included. So, in this figure, which is a repeat of the previous figure, but with the nodal location also marked. For example, you have a mesh and nodes marked. There are 2 different types of letters used, one is a capital letter and another small case letter. I is for the x direction and j is for y direction. So, in the x direction all the thick vertical lines are marked with the capital letters. So, in this case I minus 1 and I plus 1. All the intermediate lines are marked with a small case letter I and I plus 1 and I minus 1. u velocity sits between two vertical lines as shown here. Now, if you go in the j direction, j is capital J is used, and next thick horizontal line is marked as j plus 1. Similarly, the adjacent thick horizontal line is marked here as a j minus 1, and small case letters, for example here small j is referred for dashed horizontal line. Similarly, for j plus 1 and j minus 1. So, to locate a node that is given as P here as a pressure node, we have capital I comma capital J. The phase on one side phase is small I and capital J, because you are on the same horizontal line, and you move to the other side, right side, you have small I plus 1 and capital J. Now, if you go vertically, I comma capital J is here, and you go vertically up, capital I is retained because you are on the same vertical line, and small j plus 1 and I j minus 1. Okay. And you can get idea of all other important points, and in this figure the u velocity is from left to right, and that is shown in the red color, and v velocity is from top to bottom, that is shown in this color. And as we did before, u cell is shown between two vertical lines in the staggered arrangement, v cell is shown between two horizontal lines in the staggered arrangement, and pressure or scalar is marked as shown here in the original grid lines between two horizontal and two vertical. Now, this index, please make a note, because we are going to use this extensively in explaining the simple algorithm, that is small case letter and capital case letter. So, in some situation, instead of using small case and capital, they may use half. So, for example, I plus half, I plus 1, I minus half and I minus 1. Similarly, j plus half, j minus half, j plus 1 and j minus 1, any method you can follow. Simple algorithm was put forward by Patankar and Spalding in 1972. It is basically a predictor and corrector procedure for the calculation of pressure on the staggered grid arrangement. Staggered grid and corresponding arrangement of variables is used, and we explained just now through 2 slides staggered arrangement of variables. Neighboring nodes coefficients are marked as A NB subscript, and NB stands for neighboring nodes, and pressure can be discretized. Now, we have the Navier-Stokes equation. So, you discretize all the terms, convection term, viscous diffusion term and pressure term. Pressure is also discretized by following a procedure, and coefficient of pressure after discretizing is denoted by A I comma j. So, the momentum equation after discretized on the staggered grid is rewritten in this form as shown here. So, A I comma j u I comma j equal to sum of all the neighboring nodes coefficients plus pressure term, discretized pressure term, plus any source term that may be there in the momentum equation. So, this equation is a generic equation, in the sense if you run the variable I and j appropriately for x and y direction from top to bottom, from left to right or from bottom to top, then you are able to write this equation for the all nodes in that domain. And this is a neighboring node, and it is brought to the right side because it is supposed to be known either from the previous iteration or from the guess value. The first step in simple procedure is initial guessing of the pressure as well as velocity component. As I mentioned in the last class, we have a domain defined, then you have a grid defined, you also decide choice of variables location, boundary condition is defined, you have to start the calculation or simulation. to start the simulation we need to make a guess. This step is called initialization. The same is followed even in simple procedure, and we call this as a guess pressure denoted by P star and guess velocity denoted by U star and V star. We are explaining here for 2 dimension, and it can be extended to include third dimension as well. So, discretized momentum equation, and we have just now seen in the previous slide, is then solved. So, once you solve discretized momentum equation using the guessed pressure, then it will result in next step what is known as the guessed velocity component U star and V star as shown here, right. Now, we can set up a equation for pressure correction P prime, and this P prime, the pressure correction, is defined as shown here. Actual pressure is P, guess pressure is P star, correction pressure is P prime. So, if you add the correction pressure to the guess pressure, that will result in correct pressure field. We follow the similar procedure for the velocity component. So, U star is a guess velocity and U prime is a correction in velocity. If you add them together, you get correct velocity field. Similarly, for the other component of velocity. So, at this point, if you subtract equation with the guess values from the equation with the actual velocities, which mean you have actually started with the guess value, discretized Navier-Stokes equation is the same. Suppose you had used the actual velocity as well as pressure field in the discretized momentum equation, and you have now discretized momentum equation written with the guessed pressure and velocity field. So, if you subtract one from the other, then you get correction pressure as well as correction velocity, and that is what is shown here. So, U I comma j is the actual velocity and U star is the guessed velocity. If you subtract the actual velocity from the guess velocity, that will result in correction in velocity value, and this is repeated for all the terms inside. So, this is for the neighboring node and the remaining for pressure, and we already defined, we use a symbol U prime. So, the left side U I comma j minus U star I comma j is U I comma j prime. So, this is correction velocity. Similarly, on the right side from the neighboring node correction velocity term and pressure term. There is one important step in this equation. If you look at, you are doing the summation of all the neighboring nodes coefficients with the correction velocity. Suppose you had actually solved with the original or the corrected actual velocity field, then this contribution term should go to 0. In other words, if you did not have any correction, there will not be any contribution from the neighbor. Actual velocity is directly related to the pressure field. So, that is what is important approximation made. At this point, I repeat that approximation. At this point, an approximation is introduced, that is summation of A n b U n b prime are dropped simply from the above equation for the velocity correction, and omission of this term is the main approximation of simple algorithm. So, once you drop this particular term, once you drop this term summation of the neighboring node contribution, the resultant equation is shown here, and we take the coefficient A I comma j because that is supposed to be known to the other side, and you define another variable, you define another coefficient d I comma j equal to A I comma j by A I comma j, and that is multiplying the correction in pressure. So, we have obtained one such expression, correction in velocity U prime. You can repeat this procedure for same u prime at different nodal location, for example u prime at I plus 1 comma j. Similarly, for other component of velocity v prime, we already defined u is equal to u star plus u prime. In the last slide, we got expression for velocity correction. Expression for velocity correction had pressure correction term inside. Now, we get the corrected velocity as shown here u I comma j, that is a corrected velocity, equal to the guessed value, that is u star, plus the correction in the velocity as shown here. We follow this procedure for all the grid points and also for velocity component v as well as w. So, we get all expression, we get expression for all corrected velocity, and we use that in the discretized continuity equation. What is shown here is a continuity equation for 2D and discretized form with the corrected velocity incorporated, and you get finally this expression. Now, if you substitute the corresponding expression in terms of pressure correction into the discretized continuity equation, then we get equation as shown here. This equation is an equation for pressure correction in the node of interest where pressure correction needs to be obtained is on the left hand side and all other terms are brought to the other side. So, this equation has a form similar to other discretized equation. The above equation is the equation for pressure correction, which is other form of discretized continuity equation. This step is what is known as a pressure velocity coupling state. So, I rewrite that equation in the standard form a I comma j as shown here, and this is the procedure that we have followed whenever we did finite volume procedure. The neighboring nodes coefficients are separately written, and the point of interest source term appears as shown here. We have used u star expression here, and u star v star, as we know, as we explained before, is a guessed velocity field. The b prime is an error in the continuity which happens because you have used guessed velocity field in the continuity equation. When you solve this equation, you get what is known as a p prime, which is the correction in pressure, and we can subsequently get correct pressure field, then velocity fields are obtained by this expression. P is equal to p star plus p prime, and u prime I comma j is as shown here, and this is repeated for other velocity component v and at all node location. So, if I put all the steps in one slide, we start with initial guesses for u star, v star, p star. The momentum equations are solved, pressure correction equation is set up and that is solved. Then you, from that step you get p prime, and that is used to obtain pressure as well as velocity. Once you use the above pressure and velocity, then any other transport equation can be solved, for example temperature or concentration. The process is repeated, all the steps are repeated until convergence criteria that you have set is satisfied. As we did in Mach algorithm, here also we set up a condition for convergence. It may be 10 power minus 3 or 10 power minus 5, it depends on problem to problem. Once the convergence is satisfied, then we quit the iteration procedure. In terms of flow chart, it is shown here. So, we start with the initial guess p star, u star, v star and any other scalar that is generally written as phi and phi star. So, you solve the discretized momentum equation, you get u star, v star, solve the pressure correction equation, you get p prime, then you correct pressure and velocity as shown here, then solve all other discretized transport equation which is meant for any other scalar variable. We are still following the same procedure as we did for pressure or velocity variable. So, following the finite volume procedure, you get generic form of the discretized equation. So, you get phi, then you set up a convergence criteria, you check whether it is within convergence limit that you have defined. If so, you can stop the simple step or iteration and move to the next step. If not, whatever velocity pressure that is obtained in this step is now used as a guess pressure and guess velocity for the next iteration, and that is what is shown in this. Set P star as P, U star as U, P star as V, and phi star as phi. So, this values are obtained just now iterated solution, and if it is not satisfying continuity, they are reset to guessed value and procedure repeats, and you can see here, go back and repeat the procedure. Okay. So, in this class we have seen one more method of pressure velocity coupling, what is known as a simple method. It is a very popular and powerful method, people have used it extensively, it is reported in many literature. Next class we are going to see two other procedure, what is known as a simple consistent and projection method. Thank you and have fun until then.